in games, we've kind of been dependent on rasterization for a very long time. So there wasn't this ability to have ray tracing. So with the recent introduction of DirectX ray tracing and NVIDIA RTX, this interoperability between the rasterization pipeline and the ray tracing pipeline is now available to us for real-time applications. That doesn't give us a full solution to the problem immediately, however. You can't just throw your rays everywhere because you do have some amount of ray budget that you've got to work with. And so the idea is that we want to figure out where we should place the rays to get meaningful additional contribution from those samples, from the ray trace samples. Yeah, so we want to kind of summarize, we wanted to take advantage of the benefits that temporal anti-aliasing gives us, but address its failures. And then second, we want to be able to work within the constraints of a real game engine, which is the reason that we used Unreal Engine for this implementation. So as an overview of our approach, first, we just run temporal anti-aliasing. This gives us one clear benefit, which is that the results will not be worse than temporal anti-aliasing as a baseline if we choose to use those results. Second, we compute a segmentation mask, which will tell us, hopefully help us identify which parts of the image temporal anti-aliasing is failing or failing to achieve quite the level of quality that we wanted. And then we replace the typical heuristics that they use in temporal anti-aliasing to try to overcome the blurring and ghosting with adaptive ray tracing. So we choose the rays and we put them where they need to be. And then as kind of an additional minor thing here, we will run FXA on some other regions, composite all of those results into a final image, and you're done. Maybe this image will help you a little more visualize. This is an image of our segmentation mask. So in the blue region, we will decide to reuse the result from typical TAA. In the yellow region, which you'll notice these are kind of around edges primarily, we'll choose to shoot a number of rays per pixel to anti-alias. And then for the red, which is a region of the screen that was recently revealed due to camera motion, we'll run FXAA and then let it use normal TA or whatever else we choose on subsequent frames. So a note about our implementation. This was implemented in a version of Unreal Engine prior to the shipping 4.22 that has the release version of ray tracing in Unreal Engine. That's because we did most of this work quite a while ago. It would perhaps be somewhat different today. And then we added the sparse ray tracing task, sparse ray tracing pass using DXR after the standard Unreal Engine TAA pass. In the ray tracing pass, we did that before doing post-processing and things like SSAO, lens flare, and tone mapping. And then for each super sampling primary ray, we also cast a single shadow ray to the sun's directional light source to create hard shadows that match the ray tracing hard shadows we were generating in earlier render passes. So we did do ray trace shadows as well. So to show you a bit of the data flow for our algorithm, over here on let me give you the legend for this. The color rounded rectangles with visualizations represent data buffers. And then the colored rounded rectangles without the visualizations, those represent operations on the data, and they're implemented as shader passes. The gray passes here are unchanged or only very slightly modified from the standard shipping in Unreal Engine. while the green passes are the new functionality we added. So really, it's the segmentation mask that we're getting from TAA, and then doing this sparse ray trace, and then blending those results back in.